Okay, so today we will quickly go through alternating current. Okay, so we will discuss about different types of AC circuit. Okay, so in a circuit there can be only a resistor, there can be only a inductor or only a capacitor, or there can be a combination of inductor plus capacitor, let us say, that is called LC circuit. You can have a combination of inductor plus resistor, that is called Lrc circuit, and the most generalized one is called the Lrc circuit. Okay, if in a circuit you have resistor, you have inductor, and you have capacitor, that is called Lrc circuit. So if you know the current flowing in a Lrc circuit, you can if you remember that equation, you can eliminate some of the terms and make it simplified. So Lrc can be, if you know in a Lrc circuit, if there is no, if you know the equation of Lrc circuit, if inductor is not present, you can just remove that inductance or capacitance or the impedance due to the like the inductive reactance, okay, or the capacitive reactance. That part you can eliminate and you can simplify the equation. Okay, so the quick recap of what is AC and what is DC. Okay, AC stands for alternating current. Okay, whereas DC stands for direct current. Okay, so what are the so in house whatever current we are using, this is alternating current. Okay, so um, in our house whatever battery we are using, so we are using we are calling it just an inverter. Okay, but we have two devices actually in our household, whatever we have the like UPS. Okay, yeah, that is called like the power backup, whatever we are using. It is a combination of a, you have a battery and you have an inverter. Okay, so what does the battery does actually? You might have studied the electrochemistry. Okay, so electrochemistry, it's what it does. It by electrolytic principle, that battery will have electrodes, and it will create kind of storage of DC voltage. So whenever power is there, you can see that in the inverter or in that machine, something is charging. It is showing it is charging now. When current is there, you can see that battery is charging. Yeah. It means battery in certain number of hours, battery will be fully charged. Okay, that time it will stop. That means charging is over. If it is fully charged, then depending on the ampere hour, the battery is the battery will have a specification. Okay, so the battery, like I am talking about the DC current. Okay, so you will have DC, you will have AC. Okay, so this DC will be like if I plot my time against voltage. Okay, so my DC means my voltage or current. Let us say voltage or current. Okay, my voltage or current remains constant with time. This is DC. Whereas in AC, my voltage or current are sinusoidal in nature. Yeah. Okay, so this example of your battery, your cells, those are examples of DC. Okay, like say example is your battery or whatever. Okay, battery. But AC, like whatever we are using in our household applications, those are all, many of them are AC only. Okay, not all, I can say. Like you have DC motor, you have AC motor. So in DC motor you will use DC. There are many devices like your mobile charger. Mobile charger, it's your mobile needs DC to get charged. Mobile, but you are connecting it to the household power supply. you will be asking, okay, you are connecting to the AC, how you are telling that it needs DC? But you can see in a mobile charger, there is inside there is a device which converts that AC to DC. Okay, so you know different types of devices in electrical, like say you have you might have heard about the rectifiers. Okay,
Yeah.
so when we have done semiconductors, you have studied rectifiers. Okay, so what does rectifier do? Rectifier, like say full AC, full AC, it can convert like
Half wave rectifier,
to half. Okay, so it will make it DC. So this is a full wave rectifier. Okay, there is also a half wave rectifier. What it will do? Half wave rectifier will convert
only half
into
cycle.
just this, and the remaining will remain null. Okay, so this is a full wave rectifier. So then you can apply, there's something called filters. Okay, so these filters you can apply and you can make this to almost similar to DC. You can make it constant with time. Like applying filters, you can make it constant with time. So so rectifier is a device which can convert AC to DC. Okay, so rectifiers are like semiconductors, whatever that we have studied, that PN junction. Okay,
Yes.
so PN junction can PN junction can behave as a rectifier. Okay, so if you put two PN diode, that is called diode, right? PN junction, that is that diode. If you put two diodes, then it will convert to, it will behave as a full wave rectifier. Okay, so rectifier converts AC to DC. Okay, similarly, inverter. Inverter converts DC to AC. Okay, so inverter is reverse of rectifier. Okay, and so in our house we have two things. We have battery, we have inverter. Okay, so there are two things, but sometimes we call it either as inverter, or sometimes we call we just call it as inverter, but we may not realize, okay, that this battery is the more costly one, right? Suppose I have a let us say 1000 watt or 1200 watt battery. It is not like 1200 watt inverter, it is 1200 watt battery or whatever. So the battery is specified by wattage and ampere hour. Okay, you have ampere hour. So what does this ampere hour signify? Because you will have various like you will have mixie, you will have television, you will have washing machine and all. So all these equipment will consume some current, which is, they will have their own amperage. Okay, so you might have seen that your mixie or your electric iron or your washing machine, when they are when power supply is not there, you are told not to run those things, because they will consume more power or their amperage is also high. Okay, so that's the reason we bypass those things when your inverter is on. Okay, so this battery will have, it will be specified by two specifications. Okay, one is your ampere hour and one other is your wattage or watt. Okay, so you can see, I am not able to remember the exact value. Let us say your LED bulbs. Okay, these LED bulbs, maybe they are some 20 watt or so. Okay, so before these LED bulbs, whatever the conventional bulbs, that yellow color one, those used to be some 60 watt and all. So by replacing those conventional bulb by LED bulbs, we are saving a lot of power. Okay, so this LED bulb is 20 watt. Okay, let us say this washing machine. Washing machine may be in the range of, like say you take example of a pump. Okay, this pump sometimes in house will have a 1 HP pump. Okay, what does that 1 HP means? That means 746 watt. Okay, so 746 watt. That means if you have a battery of 800 watt, 800 watt battery, okay, that means only one, you can only run one pump, nothing else, okay. So that's why it consumes lot of power. Similarly, these other devices like washing machine, maybe it is some 300 watt or so. You can refer a book, okay, washing machine, or let us say your mixie or electric iron. Those will be in the range of 200 to 400 watt. We can check also. So these consume lot of power, okay. So that's why we can, and their amperage also will be high. So we cannot run them while, otherwise your inverter battery will get drained off very quickly, okay. So what this ampere hour means, like say ampere hour means suppose ampere hour divided by total amperage you are consuming. So in your house something will be of 5 ampere, something will be of 15 ampere, like that. So you add it and divide this ampere. Let us say my battery is of, let's say 1200 ampere hour, okay. So this 1200 divided by, let us say my house has some 200 ampere. That means it will last for 6 hours.
Yeah.
So in my house, if I combine all the items, okay, so all combined together is, let us say 200 ampere. So I have 1200 ampere per ampere hour. That is the battery capacity. That means it will last for 6 hours. Understand? So battery will be specified by wattage, or it will be specified by ampere hour. So depending on the amperage, how long the battery will last will depend on the total amperage of your device, all the equipment, okay. That is one thing. And wattage, like say at one point of time, what is what? It is energy per unit time, okay. So at any given point of time, you should not be operating the
more than that amount.
More than the wattage of the battery, okay. So okay, we are digressing. Okay, so that's about different device. Okay, so this rectifier converts AC to DC, whereas inverter converts DC to AC. So in our house we are using an inverter. But this battery, what does it do? Like it will take the from power supply. It will take the power supply, and you, with the help of chemical reaction, battery will have electrode and you will have an electrolyte. So that sometimes they will say, every 2-3 months you put some electrolyte. They call that distilled water, whatever. That is an electrolyte actually. So you have studied electrochemistry. Okay, in electrochemistry you have cathode, you have anode, and you have a electrolyte. Okay, so now there you are charging when the battery is fully charged.
Discharging and charging.
So it is charging and discharging. So you take when current is there, battery you will get charged. Okay, so the battery, the output of that battery is DC. Okay, so you are able to store DC. DC can be stored, AC cannot be stored. That is the major this thing. So you are able to store the DC, whereas AC cannot be stored. So you are storing the DC, and whenever power is not there, you are converting it into AC using the inverter, and you are using for your household device. So that is the difference between converter and inverter. Inverter and rectifier. There is something called converter also. But converter is which will step up or step down the DC. That is called converter.
Transformer will step up.
So AC step up, step down is transformer. DC step up, step down is converter. Okay. Something called DC to DC converter. Okay. But AC to AC converter means what? It is just a transformer. Yeah. Okay. So transformer. So these are the devices. Yeah. So what are the advantages of AC over DC? So whatever power we are generating in the power plant, finally a power plant will have a power plant, thermal power plant or nuclear power plant. Or this wind turbine or wind power plant or solar power plant or whatever. So the finally in a power plant, with the help of say wind energy or say in hydroelectric power plant, with the help of the you have the potential energy of the water getting converted into kinetic energy of the water. Okay, so finally you are rotating a turbine. You have wind turbine, you have hydro turbine, you have this normal. You will have the turbines in the power plant. Okay, so the turbine is what? Turbine is nothing but a work giving device. You will get work. Okay, so so you have a boiler, you have a turbine, and this turbine shaft will be coupled to the generator. Okay, so you will have one turbine shaft and you will have one generator shaft. Okay, these two shafts will be coupled. Okay, so there is something called flange coupling. Okay, so these will be coupled. So my turbine and this is my generator. Okay, so this normally turbines are represented by this like there is expansion happening in turbine. Okay, so this is turbines are normally represented by this. So this turbine shaft, this turbine and generator. So let us say this is my turbine shaft. So turbine shaft is coupled to the generator shaft. Okay. So turbine, whatever work it gives that in the form of rotational energy, that is getting transferred to the generator shaft. So what is there on the generator? Generator is it will have a armature and it will have some electrical windings. Okay. So what happens in a generator like that Faraday's principle? Okay. So you will have some magnet. Okay. You have some magnetic field. Okay. So you will have magnet.
Due to
Inside this
continuous
magnet,
change of magnetic
inside
flux.
this magnet you will have like say this is my generator shaft again. Okay, so so
There
this
will be continuous change in magnetic flux,
so
so EMF and current will be reduced.
So this shaft is rotating, right? This shaft is rotating. Because this shaft is rotating, that means a current, a conductor is rotating inside a magnetic field.
So magnetic flux is changing.
So magnetic flux is changing. When there is a change in magnetic flux, current will flow. That is Faraday's law. So
that current will be alternating current because every the direction will change every half cycle.
Yes.
So that is alternating current.
Yeah. So whatever power you get is alternating in nature.
And the EMF is also alternating.
Voltage, current, everything is alternating.
Every half cycle it will the direction will rotate.
Because that conductor, because it is rotating, the current and voltage will be varying, and that current will be like this sinusoidal in nature.
Like that only graph also.
So that is sinusoidal in nature. Okay, that's about the generator. So this whatever voltage you are getting, that voltage, let us say from the power plant. Okay. From power plant to substation, you will use some transformer to step up that voltage. Okay. Why do we step up the voltage? Because voltage, if we step up, the current will come down. Okay. If the current comes down, there is something called I square RT loss. That is called the heat loss. Okay. So heat loss is equal to I square RT. Okay. So this I term, if you are able to reduce,
heat loss will reduce because it's directly proportional.
Yeah. So we use different types of transformer. We use step up transformer. We use step down transformer. Okay. So from a generating station to the substation, like say thermal power plant to the substation, you will step up the voltage, right? So it will reduce your heat loss and increase your transmission efficiency. Similarly, in our village, okay, some 11 kV line might have come, some 33 kV line might have come. Okay, so that is called what is the so there at the any city or in village, they will use a step down transformer there. Okay, so incoming voltage to the transformer will be very high. Okay, and it will be stepped down there. Okay, that will be stepped down there to like say in our every household we are using 220 volt. Okay, So that 220 volt, it will step it down from very high voltage to 220 volt or 440 volt. The three phase is 440 and single phase is 220. Okay. So 220 volt and 440 volt, those kind of, it will step down from much higher voltage. Okay. So at your end of our village, there is a transformer which is a step down transformer, which is stepping down the incoming voltage which has come from a substation to some lesser value. Okay, but it has come from the substation which may be some 60-70 kilometer away. So this far it has travelled at a higher voltage, so that the heat loss is less, right?
Yes.
So the heat loss is less. So it has, they have stepped it up and they have sent that voltage. Now we are stepping it down or using it for our household purpose, right? So that's about step down transformer. And in transformer we have studied, like say we have some primary winding, and let us say we have primary winding NP, and we will have some secondary winding is NS. So my voltage, secondary voltage and primary voltage. Okay. So this relationship we know VS. Okay. Sorry, this is VP. Okay, primary and secondary. So Vs is by Vp is equal to Ns by Np. So lesser is the number of turn, lesser is the voltage. This is very, very important. Okay, but it is not always possible to. So this voltage from one side to the other side, it goes in because of mutual inductance. This is a coil. There will be some inductance. So because of mutual inductance, the voltage will get transferred from one coil to another coil. That is the principle of, that is how the transformer works. That's the principle actually, mutual inductance. Okay. So, but there will be some loss. Okay. It is not always possible to transfer 100% of the power. There will be some 90%, 80% will go. There will be some loss there in the transformer. Okay. Okay. So that is about overall, like what are the different devices and all that, right?
Yeah.
So today most of the electrical device we use require AC voltage, and this is mainly because most of the electrical energy sold by power companies is transmitted and distributed as alternating current. Okay. And so what do you mean by power company? Let's say in our state we have NTPC, okay, National Thermal Power Corporation. We have OHPC, Odisha Hydropower Corporation. Okay, so these are the power companies. Okay, so there are many private players. What I am telling, these are all government players. There are many private players, powers also, like say Adani Power or this power. There are many private players. Nowadays, many players are into renewable energy, like say solar power, wind power. Those are more preferable because this thermal power is really not preferable, because it will cause global warming, and coal if it is dependent on coal, so it can cause lot of pollution.
Combustible, it is.
When you burning coal, you are producing carbon dioxide, and it will cause greenhouse effect, and it will result in global warming. Okay, so one should avoid thermal power as much as possible. Okay, not thermal power in the sense this
Burning
power coming from coal. Okay, so it is detrimental to the environment. That's why nowadays the approach is to go more and more towards renewable energy. So renewable source of energies are solar power, and your like say India, you might have seen in UK, you hardly see sunlight. Okay, so as compared to those, our tropical nations, and let's say we are a tropical nation, similarly near the equator, so those countries, they will get good sunlight. So there we have good scope of generating solar power. Okay, it may not be that possible in countries like UK and all, or those countries. Okay, you hardly see any sunlight. Maybe out of 12 months, 9 months there will be winter, only 2-3 months. there at that time also you will hardly get that kind of sun as we see in India or any other country, right? So the main reason of preferring use of AC voltage over DC voltage is that LC voltage can be easily and efficiently converted from one voltage to other voltage by means of transformer. So another advantage, this transformer, using transformer you can step up the AC, you can step up the AC voltage, step down the AC voltage, and it is an advantage, but it is not that easy with DC. You can convert DC, but not it is not that easy as you can convert AC to AC, higher AC to lower AC. Okay. So further electrical energy can be transmitted more economically over long distances, as I said, we were discussing. Okay. So AC circuits exhibit characters which are exploited in many devices of daily use. Okay. For example, whenever we turn our favorite radio station, we are taking advantage of special property of AC circuit. So that is one example, but okay. So now we'll get into the mathematics of it. Okay. Let us say, let us go to the, so you can take a snapshot of it. Take a snapshot. So we'll go to the most simplest one, that is AC voltage applied to a resistor. So there can be different types of AC circuit. So a circuit having only resistor, a circuit having only capacitor, a circuit having only inductor, or a circuit having combination of inductor plus capacitor, or a circuit having combination of resistor, inductor and capacitor. Okay. So there can be multiple arrangement. So we will just quickly go through those things because we are you so you know this DC earlier battery we used to we used to the
Represent
AC
like
source we used to represent like this. Okay, this longer line is positive, this smaller line is negative. Okay, whereas AC source we represent it like this. Okay, so let us draw a AC circuit. Okay, so this is my alternating current, and let us say this is my resistor. Okay, so this is a resistor of resistance R, right? So okay, what is written here? With spec also I am not able to see. What is it?
Epsilon.
Epsilon. Okay, so here in this picture, a resistor is connected to source of AC voltage. Okay, it is connected to source of AC voltage. The symbol for source of AC voltage is like this because it is a sine wave. Okay, we consider source with tempered sinusoidally varying voltage. Let this potential difference also called as AC voltage. So this voltage, actually, this AC voltage is represented by, let us say, small v, we write it as small v is equal to Vm sin omega t, right? This is how we represent the AC voltage. Okay, so this voltage is nothing but we know current into resistance, that also you know. Okay, that means your current will be Vm by R sin omega t, right? Vm by R sin omega t. So this is your current, okay? Because R is a constant and this is I, so you can write I is equal to Im sin omega t. Okay.
Yeah.
Right. So that is because of Ohm's law. Okay. Voltage. So here you can see two things. So we can draw it on the right side. We can draw these things. Okay. So I remember in my 12th, in my plus 2, my teacher, S.K. Singh sir, we have in electronics, we in first year itself we had studied all these LC circuit, LRC circuit and all. So his handwriting was amazing, his pictures were amazing. He used to, with different colors, he used to draw this voltage, current, and this thing. Actually, see, he has a note, a handmade note of our senior, our two batches before us. One Sima Naik was first in Odisha, first president in Odisha. So her handwriting and notes were so good that sir had kept her notes and he was showing us those notes. Okay, in our 2 years prior to us, Sima Naik was the topper in Odisha. Then our previous batch, one Meenakshi Mahanti, she was topper in Odisha. Two girls were topper in 1987 Sima Naik, 88 Meenakshi Mahanti. But our batch, Kalidas Panda was the topper boy. But our two previous batches, Sima Naik and Meenakshi Mahanti. Sima Naik, I was that our S.K. Singh sir, because he was teaching that Odisha topper, so he had kept her notebook and he was showing us. See how beautiful her handwriting and notes are. Sir is also like his handwriting, his notes are like printed handwriting. Sir was teaching us electronics. I had 200 marks of electronics. Okay, so in electronics in first year itself, this LC, LRC and all will come in second year physics. But because we had electronics, sir had already taught us these things in electronics itself in first year. So we studied it twice, LC, LRC and all. Okay. And so okay. Okay, fine. I think we need not be accurate. So let us say this is my voltage. Okay. This is my V max. This is V max. This is voltage. Okay. So you can draw current also, and it will be okay. I am very poor in drawing. So this red one is your current, okay?
Yeah.
Whereas this this green one is your voltage, okay? So this green one is your voltage, okay? So this sine wave, the green sine wave represents
Voltage.
variation of voltage with time, okay? Variation of voltage with time, whereas the red one represents variation of current with time, okay? So here you can see like just suppose let us say let us talk with the help of numbers, okay? Let us say my voltage, let us say my household voltage, okay? how much is my household voltage actually. So V is equal to actually Vm sin omega t. Okay, right? So Vm is what? V max, right?
Yeah.
This is max.
Yeah.
V max sin omega t. So let us say in our house we are telling my voltage is 220 volt. So is it V max? No, it's not V max.
By root 2.
So this is V max will be will be 220 into root 2. Okay. So actually this 220 volt is nothing but VRMS. We call it as RMS. Root means square voltage. Okay. So whatever we are actually when you see this alternating this thing, when you see this alternating this thing, somebody will ask you what is the voltage. So if you take the mean, a sine wave mean is 0.
Yeah.
Okay. So what you have to do is you have to just square it. Okay. So when
RMS
you square
value.
it will become something like this.
Yeah.
A negative will also become positive. So that's why you have to use root mean
RMS.
square value. So what the RMS stands for?
Root
You
mean
come
square.
from the back.
Right.
Okay. First you square it.
Then take mean, then take
Square, mean, and then take the root. Okay.
Yes.
So it can be derived that whatever we are telling my household voltage is 220 volt. That means that is a RMS value. Okay. So this VRMS is equal to Vmax into root 2, right? Sorry, Vmax by root 2.
By
Okay?
root 2.
By root 2. Okay.
For
So your
Vmax,
Vmax
we have
is
to
equal
multiply
to
by root
VRMS into root 2.
2. Root 2.
Into root 2.
Yeah.
So let's say 2 Vmax is equal to 220 into 1.414 or whatever, right?
Yeah.
So it will be some 310 or whatever.
Yeah.
So that's the thing. So why is it required to take the square? Because without taking the square, if you take the mean, it will be 0, right? So that's why you should take the RMS value. These things will come in your exam actually. They will ask, okay, if this is the RMS value, then what is the max value? Okay, so those kind of things simple things will come actually in your objective type question. These are very simple things. One should never leave those things. As compared to a complicated pulley problem in mechanics, where you will have to spend more time. Definitely, see, those are interesting problems, but in terms of time management, those are interesting, but you'll have to spend more time. But these things you don't have to spend more time. That's why you need to concentrate more. Anyway, you know in your G you will do J you may do maybe 50%, 40 to 50%. If you do, you'll have a good rank. Okay, right? So when you are targeting for 40%, you should try the ones where you have to spend lesser time. Okay, so okay. Okay, so here what you can see, like this is my 0, this angle is 2 pi and this angle is my pi. Okay, so it varies from this, and I can write my V is the instantaneous voltage. So whatever I am writing V, that is called instantaneous voltage. In AC we call it an instantaneous voltage, is equal to V max sin omega t. Okay, so when this time is equal to 0, okay, when my time is equal to 0 and my phase angle, okay, say phase angle is pi by 2, phase angle is 0, okay, so my voltage will be equal to 0. So you can see at the beginning my voltage is equal to 0, but when my time is such that my phase angle, like say omega t, right? It is omega t.
Yeah.
When omega t is equal to pi by 2, then my V become equal to V max. Right? So here, this is at this point. This is pi by 2. And this is 2 pi. And this is 3 pi by 2. Correct?
Yeah.
So this is how with So here you can see this voltage and current are in phase. See, they are not out of phase. When this phase is 0, this phase is 0. When this phase is pi by 2, this phase is pi by 2. This phase is pi, this phase is pi. So that's why in a resistive circuit, voltage and current are always in phase. Okay, that is a very important thing. Okay, one of the very important thing. Okay. Okay. Okay, then so you know that Joule heating is given as I square R. So uh, okay, so voltage when, so if you say the average current is equal to 0 or average voltage is equal to 0 in AC, but that does not mean that average power consumed is also 0. That does not mean that the power consumed is also 0. It does not mean that. Okay, does not mean that average power consumed is 0. Okay, so average voltage is 0, average current is 0, does not mean that average power consumed is 0. Okay, because power is I square R, right? You know, by power is I square R. So what is power? Power is equal to, in this case, because it is AC, it will become Im square, like mean current. Okay, mean current Im square R sin square omega t. So this much power is getting consumed. So when somebody so this is the instantaneous power dissipated in a resistor. Okay, so you know power is equal to I square R. Okay, so I know my power is equal to I square R. So somebody will ask you, what is the instantaneous power dissipated in a resistor? That is nothing but your I square R, and I you know as I max sin omega t whole square, right?
Yeah.
Then R. Okay, so that is I max whole square sin square omega t R. So this is the instantaneous power consumed in a resistive circuit. Okay. Okay, so it is being written what I have discussed already related to RMS stuff. So to express AC power in same form as DC power, okay, a special value of current is defined and used, which is called root mean square power, root mean square current. Okay, RMS. So this power, if you want to equate it to DC power, you have to write it as I RMS square R.
For DC in terms
In terms of DC. Okay. So if you want to equate, so this IRMS is effective current. So DC current is otherwise called as effective current. So if you want to write AC in form of DC, you have to bring in the term RMS value. Okay. So any instantaneous power consumption is equal to I max sin omega t whole square into R, which is equal to IRMS square R.
IRMS square.
So this RMS value, so IRMS is nothing but I max, IRMS is equal to I max by root 2. Right?
Yes.
So let us say in our house, actually it will be something around 310, that is the max power, right? But 310 by root 2 will be something around 220. So just remember, when you divide
RMS value.
when you divide something by root 2, it will be 1 by root 2 is equal to 0.707.
Yeah.
So it will be 331 into 0.707. That will be something around 220, right? So that is the relationship between RMS and max, which is important, always important to remember. Okay. Similarly, voltage also. So Vrms is equal to Vmax divided by root 2, which is nothing but Vmax into 0.707. Correct. So yeah, it is given here in your book. Okay. So it is customary to measure and specify RMS values of AC quantities. Okay, when you say 220 volt, means it is RMS value. Okay. For example, the household line voltage is 220 volt, which is RMS value, and its peak value is 220 into root 2. So 220 into 1.414. Just remember, root 2 is 1.414 and 1 by root 2 is equal to 0.707. So these are the things you should remember. Okay. So the household peak voltage is 311 volt actually. It is when we are whatever we are telling 220 volt, that is RMS value, but peak value is 311. Okay. So in fact, RMS current is equivalent DC current. Okay, it's equivalent DC current.
Yeah.
DC current that would produce same average power loss as an alternative current.
Understood.
So equation can be written as P is equal to V square R or V square by R or IV or whatever. So this power, either it is V square by R or IV or whatever. So these are all RMS values, right? So if you solve on numerical, you can take a snapshot. Is it clear till this point?
Yes.
There can be good number of numerical on this. So we will solve one numerical of a resistive circuit. Okay.
Okay.
We will just solve it. How many minutes it is?
47.
47 already. Yeah? Just I'll finish one numerical in 2 minutes. We should restrict it to 1 hour, otherwise it will be too long. We will have one more session for just quickly we'll go through LC, LRC, all those things, so that in 2 classes full complete AC will get over. Okay. Now you understand the difference between AC and DC, na?
Yes.
I talked over theory, so before getting into the mathematics. Okay. So the numerical is like this. A light bulb is rated 100 watt. So we have a bulb. Okay. So bulb is power is 100 watt, and voltage, it is specified voltage is 220 volt. So it will operate with 220 volt supply and its wattage is 100 watt. Find the resistance of the bulb. Okay. So what is the resistance? So let us say this is my bulb. Okay. So so this bulb will have a resistance. Okay. So because of resistive heating, it is glowing, right? So I have a AC current supply. Okay. So this is my bulb. Okay. So they are asking its wattage is this, its voltage is this, then what is the resistance of the bulb? So we know R is equal to V square by power we know, voltage we know. So R is equal to voltage we know is equal to power is equal to I square R, right? Power is equal to I square R. Okay. And then voltage square is equal to I square R square, right? I square R square. Okay. So resistance will be V square by P, right? So my resistance will be here 220 square divided by 100, right? So it will be 444, right? 0 0 cancel. So my resistance is 484.
484.
484 ohm, that is my resistance. That is one answer. Then the next is the peak voltage of the source. Okay, what is the peak voltage? So whatever we get in our house, that is 220. So they are asking what is the peak. So this is nothing but your VRMS.
Yes.
So what is peak voltage? So V peak or V max is equal to VRMS into
sin
root 2.
omega.
No, I am asking peak now.
bar.
VRMS into root 2. Okay. So it will be 220 into 1.414.
Oh yeah.
414. Right. So this is my peak voltage, which is something around 331 or whatever. Okay, 311. Sorry, just remember this. One should remember 220 and 311. Peak is 311. RMS is 220. Whatever we are telling is RMS only. Okay? That is the second part. Then the third part is the RMS current through the wall. Now we know the RMS voltage. Okay, RMS voltage is 220. Then what is RMS current? So IRMS is equal to VRMS by R. Right?
Yeah.
So VRMS is 220 and the resistance is 484. Right?
Yeah.
If this is the case, then 220 by 484 is nothing but just 0.454 ampere. So this is a perfect example.
So for V peak, we should always multiply by root 2. That's it.
To find peak, you multiply by root 2.
Okay.
If peak is given, divide by root 2 to find the RMS. Okay.
Yeah.
So this is a perfect example of a household bulb example. Okay.
Okay.
This is real practical example.
Okay.
220 volt is our supply. The resistance you can see it is it's like 484 ohm.
Wattage is 100.
Wattage is 100. That is also we have seen 100 watt bulb, 200 watt bulb. So more is the wattage, more it will glow and more light it will make. Okay. So earlier we know in our villages when any festival will be there, they will put a very high wattage bulb, 200, 400 watt bulb. So it will make a lot of light, but lot of power
consumption. Yeah.
Okay. Before this advent of LED bulbs and all. Okay.
Yeah.
So then so you can see that my current is just 4.454 ampere. So you can see that amperage is the amperage is very less, less than 1 ampere. Whereas your mixie, your washing machine, they will have more amperage.
Yeah.
So like this. So let us say you have 100 bulbs in your house. That means it will be 45 ampere. Okay.
Yeah.
So if your battery is of 45 ampere hour capacity, that means 100 volts will glow for 1 hour. If your battery capacity is 45 ampere hour, so we'll see how much is your battery capacity.
Yeah.
Depending on that, you can do this. Okay, you can think that how long my battery is going to last.
Yeah.
Depending on the amperage, right? So two things: one is wattage, one is ampere hour. So at any point of time, the wattage consumed should not be more than watt. So by chance, you might have seen like you have put switched on many devices, which is more than the wattage of your battery inverter. In that case, suddenly there will be a trip.
Like when you use iron or anything like
suddenly, if you by chance unknowingly you are putting the electric iron, putting on the electric iron, suddenly there will be a trip because the requirement is more than the supply, so it will be tripped.
Yeah.
So that's the thing. Okay. So then relationship between voltage and current, that is represented as a phasor diagram. That is called a phasor diagram.
That is a derivation.
Phasor diagram in AC, there is something called phasor diagram. So what we do is like say your voltage. So with respect to horizontal and this axis, how the voltage is being represented. So this angle will be omega t. Okay. So the vertical component of this voltage, let us say this voltage is so it will be a rotating vector, and if this is the value of V, okay, the component of this vector will be V sin omega t, right? If this is a voltage of magnitude V, it will keep on rotating. So the omega t will get changing. So the component of that vector will be V sin omega t.
The phase angle will be changing.
So that is like say this will be like Vm or V max sin omega t. Okay. So this magnitude of this is V max. This is magnitude V max. So it will keep rotating and its component on the y-axis is nothing but your. So from the phasor diagram, if you draw a vector, its component on the y-axis is your voltage. So this phasor diagram will be more useful when in inductive circuit or capacitive circuit, where I was telling you, like in inductive circuit, just as a thumb rule you remember in your entrance, these things will come. Okay. So the voltage will be ahead of current by 90 degree. Okay, voltage will be ahead of current by 90 degree in inductive circuit.
Yeah.
Okay. In capacitive circuit,
it will lag.
voltage will be lagging current by 90 degree. Okay. And whereas in resistive circuit, voltage and current are in same phase. So when you have a LRC circuit, it depends like the resultant of inductive voltage and capacitive voltage. Depending on that, your phase angle will be decided. But in pure capacitive circuit, voltage will lag current by 90 degree. In pure inductive circuit, voltage will be ahead of current by 90 degree. And in LRC circuit or LRC circuit or RC circuit, it depends on the voltage.
RC also.
RC also is there.
But in RC also
RC also it will lag
because resistance it will be in phase.
Resistance it will be same phase. So in RC or capacitive or RC circuit,
will be capacitive
LR or L circuit, voltage will lead. But LRC it depends on the relative magnitude. So that phase angle.
LC also it depends upon.
So and that phase angle generalized equation.
Tan inverse is equal to XC minus XL by R.
That phase angle will be there for LRC circuit actually. So so that is LRC circuit. The phase angle will be XL minus XC by R. Okay. So that is the phase angle. So if XL is more, then voltage will lead current. If XL is less, voltage will lag current. So just remember, like you will confuse between inductor and capacitor. Just remember that in inductor voltage will lead. In inductor voltage will lead.
So
if you remember that, capacitor is opposite.
Understood.
In inductor, voltage will lead current by 90 degree. In inductor, voltage will lead current by 90 degree. In resistor, voltage and current are in phase. In capacitor, voltage will lag current. Okay. And in LRC circuit,
phase angle
the
is
phase
XL
angle
minus
is
XL.
dependent on the magnitude of reactance. Reactive impedance or capacitive. The impedance, it depends on the capacitive impedance or the reactive impedance, whichever is higher. Okay.
Yeah.
Actually, there are two terms. One is inductive reactance, capacitive reactance. If they are combined together, that is called impedance. Okay. So see this, whether it is inductive reactance. Okay. I was telling you, XL is equal to omega L, right? So that unit is also ohm. Okay. Inductance unit is Henry, but omega L, XL, reactance unit is ohm. Capacitance unit is
equivalent of resistance.
Capacitance unit is farad. Okay. but capacitive reactance Xc is equal to
ohm.
1 by omega C, which is again ohm. Okay, whether it is omega L or 1 by omega C, all units are ohm. But to make the units consistent, normally the inductance will be given in some millihenry, or capacitance might be given in some microfarad. So you will have to multiply it into the required number to bring it to Henry or Farad.
SI.
They are consistent unit. Ohm, Henry, Farad. They are all consistent unit. So to solve a problem, first you have to bring everything into consistent unit, then only you will solve. So omega L, which is XL, which is inductive reactance, or XL or XC, which is 1 by omega C, which is capacitive reactance. They are all unit is ohm. Okay, so we will cover LRC and other things in another session. Thanks.